So today we're going to keep talking about exponential functions. So let's just review a little bit. So we have covered polynomial functions, right? Polynomial function of degree n. We said a constant function is polynomial of degree 0. Linear function is polynomial function of degree 1. Quadratic functions are polynomial function of degree 2. Then we covered rational functions. Rational functions, which is a function with a numerator being a polynomial function, and also denominator to be a polynomial function. So then last class, we started to talk about exponential functions. And today, we're going to talk about a special kind of exponential functions, which we will start with the number e. Number e we call Euler number. Let's first, to learn what is this Euler number e, just like a pi. Okay, let me see. So people have questions. No, we're not presenting today. Keep it for next class. We'll present next class. So this Euler number e is defined as this. It's 1 plus 1 over n raised by n. N is a natural number. What's natural number? Natural number is counting number. Okay, when we see natural number in math, that means counting number. Okay, so how do we count? We start with 1, right? We would count 1, 2, 3, 4. We don't start with a negative number. We don't start with a 0. We start with 1. So natural number means counting number. We start with 1. 1, 2, 3, 4. Keep going on. So that's the definition of E, Euler number. So it keeps going on. When the n to be bigger. So in calculus class, you will learn limit. So we let this n goes to infinity big. So if n goes to infinity big, 1 over n goes to be very, very small. Right? So you see this number approaches to, when we enlarge n, it becomes 2.71828. That's what I remember. The digits keeps going on, keeps growing. If you change n to be, this is 1 million. Right? If you change it to be 10 million, 1 billion, and you have more digits going on. So, but usually, we remember 2.71828, and we call this Euler number. Euler is a great mathematician in history. So he basically defined this number. Euler, okay, we call Euler number. So this E is called Euler number. So we're going to use this E as a base. All right, you see E, keeps going on. It's irrational number. All right, irrational number. The digits keeps going on, and there's no pattern, no repeating pattern. So one very important exponential function is called a natural exponential function. So the e to the x, So the function value, y value, equals to e to the x. If you have difficulty to remember e, just think about the number 2.71828. 1a keeps going on, all right? And what's the graph of this function? The graph of this function is like this. You see, e to the x is the red color, comparing to e to the 2x, and the e to the 3x, 3 raised by x. It's in the middle, right? It's very close to 3 raised by x. Because e equals to 2.71, right? Very close to 3. So that's a graph of e to the x. Well, e to the 3 is just e times e times e, right? Then e to the negative number, that means 1 over e to the number, e to the 0.53. Okay, let's see the transformations of natural exponential functions. So first we have e to the negative x. E to the negative x means 1 over e to the x, right? Because remember, 2 to the negative 1 means half. So e to the negative x means 1 over e to the x. Maybe let me write here. So the base 1 over e is 1 over 2.71828 is less than 1. If it's less than 1, so this is exponential decay. So e to the negative x is a reflection of e to the x with a line of symmetry of y-axis. You see the blue color is e to the x, the red color is e to the negative x. Both graph passing through the common point, 0, 1. 0, 1. So that's how we usually draw a graph, exponential graph. All right. Let's see the second one. Second one is 3 e to the 0.5x or e to the half x or 3 radical e to the x, right? Remember half means radical, square root. So what is the graph? The graph we see here, if x is 0, we see here x is 0, we get 3, right? X is 0, e to the 0.5 times 0 would be e to the 0. E to the 0 would be 1. 1 times 3 would be 3. So this, we have this point, 0, 3. So this point is 0, 3. Then we give a couple more points, right? So square root of e is still bigger than 1. So it's still exponential growth, right? It goes this way. So how do we use this e to the x function? We use it in life. As last class we talked about the compound interest rate. Right, let's review a little bit. So that's how we use in life. We apply compound interest. So this is a formula. Amount of money after certain years equals to the principal. The amount of money we put in the bank multiplied by parentheses. Inside the parentheses of 1 plus the annual percentage rate, interest rate, divided by how many times compounding, then raised by how many times compounding multiplied by year. Right? That means the total compounding times. But now, so this we can talk about n, equals to 1, compound annually. Compound means calculating interest, then add the interest to your principal. We can compound twice a year, we can compound fourth a year, so that means n equal to 4. We can compound 12 times a year, means monthly. We can compound every day. We can calculate the interest every day, then add the interest to the principal. N will be 365, so on and so forth. What if we said compound continuously every second compounding? That means as long as the money in the bank, it keeps generating interest for you. It keeps generating interest for you every second. So it means continuously compound. There's no finite times. There's no more n. It's just keeps going continuously. N equals to infinity in this case. Right? In this case, n equals to infinity. That's one way you can think about it. So infinite many times. Then we use this. We use E raised by R times T. All right, the interest rate times the years, number of years, the money in the bank. So this is continuously compounding formula. So the principal times E, Euler number, raised by annual interest rate, which is R, times the time, usually is years, number of years. Let's see this example. So find the amount after 3 years if $1,000 invested in the interest rate 12% per year, continuously compounded continuously. So we use this formula. So A of 3 after 3 years that equals to 1,000. Right? That's how much money. That's the principal times the E raised by the interest rate, 12%, which is 0.12, times how many years? 3 years. So that's 1,000 E to the 0.13. If you would put an E to the E raised by 0.36, we get a number. So it's approximately this much, 14. If we put $1,000 in the bank, and the bank offers 12% annual interest rate, and after 3 years, if the bank compounds the interest continuously, after 3 years, we would have $1,433 in the bank. All right, so that's this formula. So because this is similar to the previous class, so I'm not going to go over this, but maybe I'll give you some homework, because this is still talking about exponential functions. All right, so homework 9. Let me mark here. Let's see. So you need to know the graph very well. So e to the x. Let's see, 7, 9. Oh, A is also good. A, 9, 11. 11 is good. 13. All right, let's see how many. 5. 1, 2, 3, 4, 5. Right, I'll leave this 5 as homework so you can show your work next time. So we're going to talk about the logarithmic functions. Okay, I said exponential functions and logarithm functions, like, very closely related. So here, right, let's look at this. So this is important to remember. So we can write a to the y equals to x, or it's same to say log a x equals to y. Now let's use our notation first. So we'll get into that. So far we have this. We have f of x equals to e raised by x, right? Or 3 raised by x. Let's use doubling, 2 raised by x, or e raised by x. So this one I can write f of x as y equals to 2 raised by x. I can rewrite this as this. I can rewrite as x equals to log base 2, and the value is y. So this log means this 2 is base. Okay, log base 2. I'll explain what that means. So basically, of exponential function, we can write as log function. We can write as log function. All right, let's go back here. So if I have f of x equals to a raised by x, let's look at this one. F of x equals to a raised by x. Remember a can be any number. Any positive number. A is any positive number, all right? But not 1, because 1 raised by anything would be 1. It's not interesting. So a is positive, but we don't want a to be 1. And we can talk about its inverse function, right? F of x equals a raised by x. And we can think, x equals to inverse of f of y, right? And we change the notation. So let's write the first step. So we can think about its inverse function. Inverse function will be x equals to f inverse of y, right? Then we change the notation. This is like f inverse. This is basically the inverse function. We change x and y. F inverse of this. Let me put this on the side. So basically, when we talk about inverse function, remember we talked inverse function before, right? If we have a function f of x equals y, we solve for x, then we write in the case of, so this is a -1. F inverse, f inverse is f raised by -1. That's the inverse of f, inverse function of f. Okay, so we can write this way. So same thing for here. So f of x equals a raised by x. We can write as this: f inverse of x equals y, or switch the notation, x equals to f of y. So we do this for these exponential functions, right? If we have ax raised by y, then we can write as log a y equals to x. Then we switch the notation of x and y because we want to write as a function. So we write as a function, we write this one as f of x. So basically another function. Basically, we just want to show this is a function f of x. So now we have logarithm function. So this is log function. F of x equals log base a x. All right. If we equal f of x equal to y, so whenever we get confused with this notation, we can think this way. That means the base a raised by y equals the value x. So whenever we get confused, we can write this way. Let's give a couple of examples. Right here, okay, this is very useful for in the beginning. So log base a x equals to y. We can write as base in the log is a base in the exponential function. Okay, still base. So a raised by y equals to x. So this two means exactly the same thing. All right. So whenever we get confused with this notation, we can rewrite it. We rewrite as this to help us to understand what does this mean. So this y is exponent. Okay, this is important to remember. This y is exponent. So a is base, stays to be base. Y here is exponent. So y here is exponent. So log give us the exponent of the base. Let's see some examples. So 10 raised by 5 equals to 1 following by 5 zeros, right? We can rewrite this as log base 10, then the value, 100,000, that equals to 5. Okay, base 10, still base 10. Log is exponent, 5 now becomes exponent of 10. Then this is the value, so 100,000. Let's see, 2 to the 3 equals to 8. So we can write as log base 2 of a equals to 3. That means base, still base 2. Log value is an exponent, so that means 2 raised by 3 equals to 8. Log base 2, 1/8. equals to negative 3. That means 2 raised by negative 3 equals to 1/8. 2 raised by negative 3 equals to 1/8, right? Because 2 raised by negative 3 is 1 over 2 raised by 3. 2 raised by 3 is 8, so that's 1 over 8. Log base 5, s equals to r. We write as 5 raised by r equals to s. 5 raised by r equals to s. Now let's use natural logs. Natural logs, so let me write on the side first. So we use ln. ln equals to log base e. Okay, that's what it means. We don't see e here, ln, but ln means log with base e. So if I write ln here, ln, let's see, ln, maybe I'll write x equals to y. All right, ln x equals to y. So that means I can write here e is the base. Ln means log base e. E raised by y equals to x. All right. So you see, the first column is logarithmic form, right? The second column is exponential form. So we can write one in terms of other, by switching the places, the positions. Okay, so with exponential form, we can write as log form. With log form, we can write as exponential form. Let's see these ones. So this is log base 10, 1000 equals 3. Why? Because 10 raised by 3 equals 1000, right? Log base 2, 32 equals 5. Why? Because 2 raised by 5 equals 32. Log 10, 0.1 equals -1, because 10 raised by -1 equals to 1 over 10, which is 0.1. Log 16, 4 equals half, because 16 raised by half. What square root of 16 is 4? Okay, we have some special properties. Those properties we need to get used to, we need to remember. Log base a can be any number, any positive number, right? Not to be 1, because it could be 1, but 1 is not interesting. So log base a, 1 equals 0. Why? Because a to the power of 0 equals to 1, right? Because a to the power of 0 equals to 1. Anything to the power of 0 equals to 1. And log base a and a equals 1. Why? Because a raised by 1 equals to a. Then this one log a, then the value is a to the x equals x. Why? Because a to the x equals to a to the x, right? A to the power x equals a to the power x. And last one, let's see why. Last one, let's write as exponential function. So that means we'll have a log. So we can write log base a x equals to log base a x, right? So a to something equals to x. That means we can write a log a raised by this equals to this. So it's obvious, right? If we rewrite it. Okay, let's see some examples. So log base 5, 1 equals 0, right? By the first one. Because 5 raised by 0 equals to 1. Right, be right on the side. Property 1, or also we can remember this. 5 raised by 0 equals to 1. This second one is 5 raised by 8 equals to 5 raised by 8. This property is very useful. This property is saying if we can make the value here with base, as an exponential, with base, with exponents, and the base happen to be the base of log, and that cancel out to be 8, right? What's up here is 5 raised by 8 equals to 5 raised by 8. 5 raised by 1 equals to 5, right? Then log 5 of 12 equals to log 5 12, property 4. So log in the beginning is kind of confusing. So make sure you understand these examples, read a couple of times to train your brain from one way to another, right? Give you a log, read into exponential form. Give us exponential form, read into a log form. Once you do a couple of times, you can get used to it. So graph of a logarithm function, right? So remember this blue one is y equals to a to the x, or f of x equals to a to the x, right? And a is bigger than 1. So for this one, a is greater than 1. If it goes this way, a is less than 1. And its exponential function, what we can write as f of x log base a x, right? It's inverse, because inverse function has a line of symmetry y equals to x. So log function and exponential function are inverse with each other. So they're inverse with each other. So which means log is the inverse function of exponential function, or exponential function is the inverse of log function. So let's see here we said it's saying sketch the graph log 2x, right? So from now on, let's remember this log function. You see the x value started from positive values. X value cannot be 0. Excuse me. Or x value cannot be negative. So that's the domain of log function. That's right here. Domain of log function is x greater than 0. Right? We can see from this graph, we can see from the red color graph. You see x value only on this side, right? Positive values. So the graph always looks like this, okay? It passes through the common point 1, 0. We have a common point 1, 0. So log 2 with base 2 x function like this. That's the common point 1, 0. Then we can give a couple points, all right? If it's 2, if x equals 2, log 2 equals to 1. If it's log 2 4, log 2 4 equals to 2, right? Log 2a equals to 3, so on and so forth. We see some log functions. Okay, if it's base 2, we have the red color. If it's base 3, it's lower, we have this black color. If it's base 5, we have this blue color. If it's base 10, we have this purple color. Okay, if we have base E, it will be in between of those two. In between of 2 and 3, that would be base E. It will be L and X. Let's see this graph transformation, right? Negative log 2x. Well, log 2x is the blue color. And the negative means reflection over x-axis, right? So this part of blue goes down here, right? And this part of blue flipped up here. Right? We see these two graphs have reflection over x-axis. What about the log 2? Now the x be negate of negative x. That means all those positive x value now has to be negative, because negative become positive. So this is a reflection over y-axis. Over y-axis. Now let's see the shifting. We have vertical shifting, horizontal shifting. Let's see first one. G of x equals 2 plus log 5x. We know log 5x, the blue color, right, like this way. The log function always goes this way. Now, every y value be lifted up 2, because this is log 5x plus 2, right? We have 1, 0 here. Now it becomes 2. Yeah, 1, 2. Yeah, look at this point. Right? Before we have, let's see, it's 5, 1, 2, 3, 4, 5. We have 5, 1, we have this point. Now it becomes, we have 5, 1. Now 1 is being lifted up to 2, so we have 5, 3. Right? So look at the important points. Right? Let me just mark this. Because every y value is being lifted up to 2 units. So I have 1, 0. Now that point moved up here becomes 1, 2. Okay. And this point here used to be 5, 1. The base is 5. If x is 5, that means the y value is 1. And this one being moved up 2 units, that becomes this point, 5, 3. So we see every y value being lifted up 2 units. Right? So this is a vertical shift. So the first one is a vertical shift. Vertical shift. Vertical shift up 2 units. So that's the first one, A. Now let's see second one. Second one is x value being shifted, right? We see that happens inside the log. It's log base 10, then x minus 3. Minus means right shifting. Excuse me. So that will be this one, 1, 0, being shifted to 4, 0. Every x value being shifted to the right 3 units. So we have log base 10x here. We have this point 1, 0, common point. Now being shifted 3 units to the right. So it becomes 4, 0. Okay. You see this is horizontal shifting. Horizontal shifting. Okay, if you have any questions, feel free to stop me anytime. Common log. So sometimes we don't need to write this. If base is 10, so we can ignore it. We just write a log x. So it's by default. If we only write a log, log, that's log base 10. We write a log 10, that means the base is 10, value is 10, so that equals 1. Log 100 means log base 10, 100, that's 2, because 10 squared is 100. Natural log. So log base e, which is read as lnx. Okay. So in calculus class, you usually don't see any other base. We always use natural log. We use ln to represent log base e. Right? So this is for calculus class. Calculus class, we always use ln. So ln x equals y, that means e to the y equals to x, because the base e to the exponent equals to this value x. And the y to the ex is this blue graph, right? And the ln x is its inverse, this red color. So try to remember those graphs. Those graphs are very important. We call reference graph. Whenever we think about, exponential functions, exponential growth, right? When the base is more than 1, we think about this graph. If the base is less than 1, we think graph like this. For log function, we think about graph like this. So this is a reference graph. Whenever we deal with log functions, we go back to a reference graph. So ln 1 equals 0 because e to the 0 equals 1. Let's just read a couple of them. E to the 0 equals to 1. And the second one, why is true? Because e raised by 1 equals to e. And this one, the third one, we can write as exponential form e to the x equals to e to the x. Right? And number 4, exponential form e to something equals to x. We can write as ln base e. Ln is base e, right? X equals to ln x. That's for number 4. But let's see some examples. So ln e to the a equals a because this is base e, right? ln 1 over e to the 2, we can write as e to the negative 2. Then this e is the same as the base e, so that equals negative 2. ln 5, e, this is base e. We can punch into a calculator, get about 1.6 something. Okay, let's see this example. This example is saying find the domain of a logarithm function. How do we find the domain of a log function? We take the value inside, all right? We said 4 minus x squared has to be greater than 0, right? Remember the log function graph? This value, we call this value inside the log has to be positive. So 4 minus x squared has to be greater than 0, all right? 4 minus x squared has to be a positive. That means x squared less than 4. That means absolute value of x has to be less than 2. So that means x value has to be restricted with negative 2 to 2. All right, negative 2 to 2. So this is the domain of this function, this log function. Okay, let's do a little bit of practice maybe. Okay, let's try now. Try to try 2, 3, 4. Right, let's try 2, 3, 4. Let's try 2, 3, 4. Okay, I'll give you probably 10 to 15 minutes to try this. Okay, do I get someone to show? So anybody wants to show 2? Anybody like to show 2, 3, 4? Okay, Rina wants to show 2. Let me make you presenters. Tijera wants to show 3. Do I have anybody else to show 4?
Oh, since I didn't take a picture and upload the paper, can I just talk about it?
Yeah, just talk about it. So this is more to understanding.
So for the log of 9x, the function base is 9.
Yeah, let me read for you.
And then for f of 9, the answer is 1 because that's the that's how you get the answer.
Right, what can you tell us why is 1?
The reason it's 1 is because like when you write it down in the log form, it's gonna be log 9 to the 9 equals 1 because 9 to the 1 is gonna be 9.
Great, yes.
So f of 1 is 0 because 9 to the 0 is gonna be 1.
Right.
And then f of 1 over 9 is -1 because 9 to the -1 is 1 over 9.
Right.
And then f of 81 is 2 because 9 to the second power is 81.
Right.
And then f of 3 is 0.5 because 9 to the 0.5 gives you 3.
0.5, half, right?
Yeah.
Oh, 0.5, right. Because square root of 9 is right. Okay, great. Good job. And the teacher wants to show 3. If anybody has any question, just ask.
Professor, I try to upload the picture, but it's taking forever to load. So I could just explain if that's fine.
Yeah, you explain. I'll read the answer for you.
Okay. So 5 to the third equals 125. So to find the log of that, what I did is that I did like base 5,
Base 5, log base 5.
log base 5, in the parentheses 125.
125.
Yeah. And then that is equal to the exponent, which is 3.
Great. Yes. So log base 5, valued 125 equals 3. Great. Second one.
Second one, I wasn't able to do B though, because I thought it was only A.
Are you're able to do it? Remember log?
But I could try.
Yeah, try it.
Okay, so it would be 5.
5. Base stays to be base. Base in the log is base in the exponents. Either
Yeah.
exponential form.
And then the exponent is 2 equals 25.
That's it. 5 divided by 2 equals 25. That's it. It's just a
Yeah.
change the order, change the writing. Yeah. Okay, great.
Okay.
Good job. And anybody want to try 4? Okay, let's do 4 together. So 4 here, we have a f of x equals log 2x. Well, let's try to remember the graph. That's 3, okay? Log graph always goes this way. It may be a little bit lower if the base number is bigger. So this top gets lower. The bottom part is always close to the y-axis, but it will never reach at y-axis. All right, so this graph, yeah. So it has this kind of graph. So let's log 2x. Then let's say b. B is log 2. Now x is being changed. Before was a positive x. Now we have to change it to be negative x, right? Change positive x to be negative x. We just flip the x value over on the other side of y. So that gives us 2. So b is 2. Let me write it on the side actually. So a is 3. So this is a. B is 2. Because every x value is being negated, right? See the reference graph. We're treating a as reference graph. Now x being positive, right? When negating x value. So that means x value now has to be negative, because negative and negative become positive. Because inside the logs cannot be negative value, it has to be positive value. So negative x has to be positive. So what may be read this way? So for this one, the domain for this one for b is negative x being positive, it has to be positive. Inside the logs, the value has to be positive. Well, this gives x being negative, right? The negative x has to be positive, is x has to be negative. So I have this graph. Well, let's see C. C, we have negative log 2x, right? Again, treating this one. So every value of y, every y value is being negated. So before the value is above x-axis, which means the y value positive, now go down here, right? Becomes negative. And before the negative y value, now go above x-axis. So it tells us C is 1. It's the first one. Because the y value is being negated. So that's a reflection over x-axis. Well, let's see D. D is both. When negating the x value, when negating the y value. Guess what? It has to be 4, right? X value is negative. Y value, the graph is being negated. The graph is being flipped over x-axis. So the 4 is D. Convince yourself, all right? So use this as reference graph. Log base 2x as reference graph. Then consider the other 3 as transformations of this. Okay, basically, good job. Let me assign you some homework from this. So this is a part of homework 9. So I'm just adding to homework 9. So this is 4.3. So 4.3. So we did a 4.2. 4.3. Let me see. Let me choose a couple of them. Okay, 49 is a good one. And here, I want you to also do some basic calculations too. So I'm going to write 49 as the last one. Then let's see. So express the equation in exponential form. All right. So let's do 10 to 12. So 10 to 12. This one exponential equation in logarithmic. Let's do 16 to 18. 16 to 18. Evaluate the expressions. Let's do a couple of this. Let's see, 23, 26, 23 up to 26, 23 up to 26. This might be a little more, but it's good practice. 31, 29 to 33. Okay. 29 to 33. All right, so I'll write, let's see, so 4.2, let's see, 4.2. 4.27, 8, 9, 11, 13. So more on 4.3. So next class, we're going to present. Hopefully we can review all those, because this is new. It's very new to us. So 4.3, we do 10 to 12, 16 to 18, 23 to 26, 29 to 33, then 49. All right, so I'm going to write in the under the content. Okay, anybody has any questions? Oh, Sarah has a question. Sarah is asking, do we have a quiz, midterm, or final shown? Not shown, but we always have homework due, right? Homework due in a week. So focus on homework and presentation. If you are confusing with our grading policy, go to Blackboard under content, search for grading policy. So basically, grading will be on homework 40%, presentation I think it's 20%. Let's go for it. Let's review this. Are we going to have a final song? What do you mean? We're not finishing this semester yet, right?
Professor, I'm just asking so we know what to expect in the future so we could prepare ourselves better.
Okay. All right, so make sure, right, let's go to, I'm going to share my screen with you. Okay, you can see this, right? This is a CUNY Blackboard and the content. So if you click on content, it shows you this. So let's see, grading policy, 40% on homework, 40% on presentation, and 20% on final. So let's see presentation. For presentation, you may choose one from your homework to show us next class, or you may
Professor,
not
I
show
can't see
it.
anything. I'm sorry.
Or you cannot show it,
No, I can't see it.
or you cannot see it, but I share the content on the screen. I shared my screen with you. Okay, anyway, let me read for you. So you're clear on the grading policy, right? 40% on homework, 40% on presentation, 20% on final. All right, any other questions? Homework 7 about range 61 and range 63. Let's see that. Let's see. So homework 7. Can you remind me homework 7 is which section? Three point seven. Okay, right here, 3.7. So 61, 63. All right. So this question is what do we have to do? From 41 to 64, find the intercepts and the asymptotes, and then sketch a graph of the rational function and state the domain and range. Use a graphing device to confirm your answer. Remember, how do we find our range for rational functions? We use ignore rule, right? Let's see 61. Remember our ignore rule? Let me write here. Take leading term, ignore the lower term, take leading term. So what's the leading term in numerator? 3x squared, right? What's the leading term in denominator? X squared. So 3x squared divided by x squared, that equals to 3. So the domain at the range, how do we see it? Let me put over here. So this is for question 61. We'll take a leading term. Consider leading term. Consider leading terms in the numerator and in denominator, right? In the numerator is 3x squared. In the denominator is x squared. 3x squared divided by x squared equals to 3. So how do we represent this as a range? So we know this is a horizontal asymptote, right? Horizontal asymptote we write as y equals to 3. So how do we write in range? Range means y cannot be 3. Range means any number but 3. So y is not equal to 3. You don't have to use words because I do not have not equal to 3 on my keyboard. So I have to write this way. So this is for 61. Let me see if I can make it. Okay. So to find the range is the same as to find the horizontal asymptotes. How do we do it? We take the leading term in the numerator. This is for rational functions. We take the leading term in the numerator. We take the leading term in denominator. We divide them. We get, in this case, we get 3. That is to say horizontal asymptotes is y equals to 3. It's the same to say range is y can be any real number but 3. So y cannot be 3. So that's the range. But I was getting my range from the graph and I got something a little different. No, this is a range. The range, this is the easiest way to get range. All right, if you can find asymptotes, right, that means you can find the range. Range is just, remember asymptotes, horizontal asymptotes means we put a dotted line. That means this value won't be in the range, right? The same as vertical asymptotes give us the domain, right? If we have vertical asymptotes, that means the value cannot be in the domain. So similarly, if we can find horizontal asymptotes, that means that value cannot be in the range. So for 61, the range is y can be any real number but 3. 3 is not in the range because what happens in 3? Y equals 3, that's a horizontal asymptotes. Like, okay, any questions? Any other questions? Rina, if you have different answer, you have to consider your answer, right? Doesn't matter what kind of method you use, the answer should be the range is not 3, but any other numbers. Okay, any other questions? $63 is the same, right? You can figure out the 63, right? Oh, 63 is a little bit different. All right, it's good to talk about 63. 63, and maybe even, so let me give you 2 examples. So 63, the denominator has x. Let me talk about other 2 situations for range. So if we take the, 3 situations for finding horizontal asymptotes or the range. So let's list the situations. One is we get a number, right? So if we get a number, that means the numerator, the leading term has the same term. The leading term have the same, so that means that, okay, the numerator and the denominator are the polynomial of same degree. Okay, if same degree, we always get a number, which is 61, right? The other 2 situations. So what's the other 2 situations? So when we get a leading term, let's consider this one. We get a 1 over x. If we simplify, we get a 1 over x. So the numerator will get a number. The denominator will have x. Then we think this. Think x goes to infinity, right? Think x goes to be a very, very big number. So that means 1 over x goes to 0. So that means the range, that means the horizontal asymptotes is y equals to 0. It means the range is y is not 0. But every other number, every other real number. So this is one situation. Let's see another situation. So this is we have x. So this means the denominator is a higher degree polynomial than the numerator. The situation is the opposite. We may get, let's say 2, we may get x in the end, x over 1, something like that. So that means the numerator is a higher degree of polynomial. So in this case, we think about, so this goes, when x goes to infinity, this goes to infinity, right? So what's our conclusion? There's no horizontal asymptotes. So what's the range? Range is all real numbers. We have 3 situations. Okay. So if the numerator and the denominator are the same degree of polynomials, we always simplify to get a number. And that number gives us the horizontal asymptotes. And that number is not in the range. So we would say the range of that function is, y can be any other number, but not this horizontal asymptote. Another situation is the denominator is a higher degree polynomial. then that means it goes to 0. Think about x, it goes as big as infinity. So 1 over x, or fixed number over x, will be 0. So that means the horizontal asymptote is y equals 0. So range is y can be any other number but 0. Or if the numerator is a higher degree polynomial than the denominator. So of course, that means the function value goes to infinity. In that case, no horizontal asymptotes. In that case, range is all real numbers. So I have 3 situations. All right, any other questions? So for 63, 63, we see the denominator is a higher degree. Denominator with x cubed, right? If we take the leading term, we have x squared divided by x cubed. Then we simplify. When we simplify, we get a 1 over x, right? That would be the first situation. The horizontal asymptote is y equals 0. The range is any real number but 0. So this is for 63. All right, any other questions? All right, so today you have a lot of homework. And right, if you cannot finish, it's okay. So next class we'll be keep talking about these logarithm functions. All right, and you may present the next class. If you have questions, we can talk about the questions. All right, anybody has any questions? All right, if not, yeah, we'll just finish here and have a good day. Right, Sarah, to answer your question, I received someone, I'm not sure whom I received. Because for presentation, the grade is different. For presentation, if you do in class time, that give me chance to ask you questions. If you can fully answer my questions, you have potential to get 100% right for the presentation. But if you send me, I didn't receive someone's recording. First, you have to show me your face because I have to make sure that person who is presenting, it is you. This morning I received someone's presentation. I'm not sure if that's yours. It didn't show me a face because I need to match the person to the picture I have, in the garment in the file. So I have to make sure the person is the person in my class. And the second, you have to show me every step, how you get every step right. And if you send me through email, that's fine. You have to make sure you get everything right to get credits, right? If you don't get everything right, I give you grades. That grades really depends on how well you do the presentation. Yeah. So to answer your question, yes, you may, but you won't get full credit. Okay, any other questions? All right, if not, I'll see you on then. All right.